Hello everyone, my name is Chuanhua Xu, and my teammate is Yan Chen. Our topic is a low noise amplifier with accurate embedded hybrid time gain compensating for ultrasound receiver front end. First, I will give you some introduction and motivation about our system. Our project primarily focus on design a low noise ultrasonic receiving amplifier front end for diagnostic imaging application of ultrasound. As ultrasound wave travels through biological tissue and refraction, they experience exponential propagation attenuation, which may amount to 40 dB for large imaging depths, posing a significant change for receiver front-end circuit. Consequently, achieving low noise to detect weak echo and minimize gain error are the primary design focus. In this work, we propose a LNA with an embedded hybrid time gain compensation architecture for ultrasound receiver front ends. Figure 1 shows the simplified architecture of ultrasound image ASIC. The ASIC is usually composed of an array of ultrasound transducers, each of which include a dedicated receiver and transmitter. We can change the mode as the switch connects to the transmitter and receiver. Our system is focused on the receiver part. Since the ultrasound wave experience exponential propagation attenuation, prior art used a circuit that performed the pseudo exponential gain function. Higher order of pseudo exponential function will get more accurate. However, it needs to be more power hungry and complexity. So, figure 2 illustrates our main idea about the TGC system. We divide the 40 dB range to a smaller subrange to ease the circuit complexity and the power consumption. To balance the trade-off between the die area and the power consumption, the 3 subrange architecture was chosen. It means that each range at about 14 dB, means 5 times, and it achieves a theoretically gain error of 0.281 dB. And figure 3 shows that the architecture of proposed hybrid TGC LNA. It gets the current signal from the ultrasound transducer. And the first stage, we use a capacitor-based programmable gain amplifier. It separated the whole range to 3 subrange. And the second stage, we use Class AB current steering amplifier. Interpolate the first order pseudo exponential gain function, which within each subrange. And it utilizes current steering bias network to bias. Finally, we need an output buffer to push the signal out. And the figure 5 shows the topology of the first stage PGA. We use the capacitor feedback resilient resistor to reduce the thermal noise. Since we set 3 subrange and each subrange gain is 5, so C1 and C2 is about 25 times from the lowest to the highest gain setting. In order to maintain the bandwidth of the amplifier, we use the distinct C1 and C2 value razor than lying on the single fixed C1. And figure 6. Figure 6 shows the topology of the second stage Class AB current steering current amplifier. We use the Class AB architecture to enhance the current driving capability without increasing static power consumption. And we use a local feedback loop to lower the common gate input stage as a better current input. Let us see the overall architecture. The current steering amplifier composed of one input current branch and one output current branch and 6 additional current branch. The effective current gain of the amplifier is determined by the ratio of the total number of unit current branch connect to the input branch versus connect to the output branch. To achieve the desired pseudo exponential gain function across 14 dB, the number of the unit branch in the input and current steering and output stage is configured as 3, 1, and 9 separately. This configuration yields a 7 discrete current gain step, which then continues interpolate to form a smooth exponential-like gain transition. And the figure 7 shows the whole chip micrograph of our proposed system. This is a fully on-chip ultrasound receiver. Compared to prior art, our system performed the lower gain error and the input reference noise density at 5 MHz is less than 1 picoampere per square hertz. And finally, we use our receiver with transducer to perform imaging measurement. The left side of the image before using our TGC, and the right side is after using our TGC, successfully restoring the deep tissue signal and clearly visualizing the target object